Next up on our review session, fluid mechanics. Fluids or fluid mech. Now, on things like the AP exam, they have a tendency of combining fluids and thermal physics together. The way we approach them, I split them up because I think thermal physics is complicated enough that I wanted to treat it more or less as its own entity. Fluid mechanics has a couple of equations. You'll see that we end up with quite a few of them where they just kind of seem to go on and on. Now, it's hard to pick which ones are going to be the most important. Do what you can to get these down, but compared to some of the other mechanics equations, these are not as important as some of the other mechanics equations because they really only apply to just the fluids questions themselves. But I am going to show you the important ones that seem to show up a fair amount. First off, kind of important one is going to be buoyant force, the force of buoyancy. When we put something in water, for instance, its tendency to float, or, as I will remind you, even if it sinks, we still have a buoyant force. That's something that throws people for a loop. It's going to be equal to rho V displaced G. Now, when you look this up, they'll tell you that the buoyant force is actually equal to the weight of the displaced fluid. I think that that's a limited equation. It'll change into this, so I give you guys this instead. The density of the fluid you're displacing times the volume that you have displaced times the local acceleration due to gravity. Okay? So, it is in fact equal to the weight of the fluid that you're pushing out of the way with whatever you've got floating there. But this is a more useful form of that equation, I feel, than simply writing that it's equal to the weight. The next one, and this one deals primarily with water flowing through pipes. We call it the continuity equation. Now, I gave you guys that the flow rate was equal to Q, although often you are not going to see that particular variable show up, the flow rate. However, the flow rate is equal to our area times our velocity. Right? So the area, the cross-sectional area of a pipe, and then the velocity of the water flowing through that pipe, when I multiply all those together, that'll tell me how much I have flowing through there. It's usually in cubic meters per second, at least in SI. You'll find that when you look into engineering things, if you go and you find a lot of stuff set up for plumbing, they'll give you ratings in cubic feet per second, because that's the more common one for the imperial units. However, the stuff you're going to be solving, going to be in meters most likely. Now, the idea behind continuity is we can't have any of this water, if it's water, disappear somewhere in our pipe. Whatever goes in has to come back out. We're going to see the same concept shows back up when we deal with electric circuits. Whatever charge we have going in there, it can't just suddenly cease to exist. It's got to go somewhere. So, if I constrict my area, I make it smaller, for instance, then my velocity has to get higher. The water has to move faster through there because we've got a whole bunch of stuff coming in that still needs to get through. This is our continuity equation. The area, the cross-sectional area of the pipe, times the fluid flow through it, or the velocity of our fluid, equals some constant number throughout that pipe. Whatever water we have coming in has got to be the amount of water that we have coming back out, because water doesn't just disappear. Next one, and this is a very good equation. This one's kind of fundamental. In fact, I almost left it off the list, but I want to make certain that we have it, because I'm afraid I almost left it off because it seemed kind of too straightforward, but we're not going to take that chance. Force, or I'm sorry, no, I've got it slightly different. Yes. Pressure equals force divided by area. And this is another one that we see that comes up in thermal physics, one of the reasons that these are kind of put together. Okay? So, again, we've had certain things that come up time and again in different aspects of physics. They all kind of work together. I just mentioned continuity shows up in electricity and magnetism, although instead of water, it's charge. So these concepts, they build off of one another. Try and build those connections as much as you can. Knowing this here helps you when you have to deal with it in thermal physics as well. The pressure is going to be whatever the force that's applied divided by the area that it is applied over. Okay? So, the next one that I'm going to have listed in here is pressure at a given depth in a fluid. This was one of the first ones we started with. We always found out what the pressure was at the bottom of a pool. Well, we have that equal to our initial pressure. Basically, normally this is our atmospheric pressure, because our pool usually has the atmosphere above it. Plus rho g h, where rho is the density of our fluid. We usually dealt with water, so that's 1,000 kilograms per cubic meter. G is the acceleration due to gravity, so that's going to be 9.8 near the surface of the Earth. And h is going to be how deep you are in that fluid. If you're 10 meters down, then you put in 10 here. If you're 1,000 meters down, you put in 1,000, right? So you could find out the pressure on a submarine when it dives down beneath the waves. That was another thing that we looked at, the Buoyant class, if you remember correctly. Check for it in your notes. Now the last one that I'm going to put on here is the Bernoulli equation. We did a little bit with this. It comes from conservation of energy. We have some pressure here plus rho g y. That deals with pressure that we end up getting from a given depth. Plus 1/2 rho v squared. And this is going to be equal to a constant most of the time that you end up using it. It's an energy balance. So you're going to find that something happening on one side of your pipe is, you'll fill in the values for this, and you'll set that equal to what's happening on the other side of your pipe. The pipe may raise up, may go down, maybe it goes upstairs to a second floor, maybe it's from a water tower. And so your first spot is at the top of the water tower, and your second spot is at the valve at the bottom of the water tower. As a hint, that may or may not have been one of the main problems that we solved when we went over the Bernoulli equation. So that can be one of the places where you can see its applicability. Key things on this, I don't have too much to fill in on this. One of the big things that I wanted to mention again, though I said most of it up to this point, is continuity. The idea that your water can't just magically disappear partway through. Make certain that you keep that concept on hand, because that is a fundamental concept for physics and for chemistry. It's technically what the chemists call conservation of mass. We don't have stuff just disappear somewhere, right? So that one's important, and it's also a good one to have on hand because we're going to see it applied in electric circuits. The other thing, and this is one that I want to emphasize a bit because it's easy to overlook. When people deal with buoyancy, they forget that that buoyant force, when you look up here, it is equal to the weight of the fluid displaced. Many people think that you only have a buoyant force if the thing is floating, which is emphatically 1,000 times not true. You have something submerged and it is displacing liquid, there is a buoyant force. I showed you in class, I actually had a weight, and I had it on a scale, and the scale read something, and then when I put it down in the water, the thing was made out of steel or something like that. So it sank. Oh, it sank. It was not floating, but the scale actually adjusted where it said that it weighed less. There's a buoyant force because that metal was displacing a fluid. There was a net force helping to support that weight. Okay? So please, please, please remember, buoyancy, the buoyant force, applies no matter what, as long as you are displacing some fluid. It doesn't matter if it's floating, if it's sinking, or whatever it's doing, there is a buoyant force if you are displacing fluid. That is a key thing that a lot of people overlook.